You probably learned that on the periodic table, a group refers to a vertical column, and the elements in a group share certain physical and chemical properties. Now, I've left off the F block on this picture, but perhaps you recall that most of the elements, including those of the F block, which is down below the main body of the periodic table, are metals. There is a triangle on the right side that includes the few nonmetals, as well as in the upper left hydrogen. Hydrogen is a nonmetal. And then in between the metals and the nonmetals we have some kind of metal-like but kind of nonmetal-like metalloids. There's a little bit of debate as to which elements exactly are the metalloids, but generally they're this little stair-step group of elements in between the metals and the nonmetals. You should know that the group 1 elements are called the alkali metals. So that would be all of those elements on that side. Hydrogen is not an alkali metal. Even though it is in group 1, you should not think that hydrogen is an alkali metal. It is not. The group 2 elements are the alkaline earth metals. The group 16 elements, which include oxygen, are sometimes called the chalcogens. And perhaps you remember that the group 17 elements are called the halogens. Again, there is a little debate about whether this bottommost element in group 17, which is astatine, there's a little bit of debate as to whether that should be considered a halogen or not, but I consider it a halogen just for fun. And the group on the far right side of the periodic table is called the noble gases. Molecular compounds contain only nonmetals, no metals at all. Let's define empirical formula. An empirical formula shows the relative numbers of each type of atom in a molecule. This empirical formula shows that for every one carbon atom we have 2 hydrogen atoms. Now, the empirical formula doesn't tell us the precise number of carbon atoms or the precise number of hydrogens. It might be 1 carbon and 2 hydrogens, or it could be 2 carbons and 4 hydrogens, or 3 carbons and 6 hydrogens. All an empirical formula tells us is the ratio. The molecular formula shows the actual number and types of atoms. This molecular formula, C3H6, would have the empirical formula shown above it, CH2. When we say a structural formula, we're talking about a diagram that shows which atoms are bonded to which. For example, here is a structural formula. If you're already familiar with the Lewis structure, a structural formula is exactly like a Lewis structure, except structural formulas don't show unshared pairs. If that didn't make sense, up to this point, it's okay, don't worry about it. I'm going to cover it in a future unit. There are also other ways that we can represent molecules. Here's a perspective drawing. The straight line indicates that those bonds are in the plane of the picture. The triangle here that's dark represents a bond that's coming out towards us, and this little dotted line represents a bond that is actually further away from us, so that there is a three-dimensionality to this perspective drawing. A ball and stick model looks like that. Many first-year students build molecules in class using a ball and stick representation, and then a space-filling model tries to account for the idea that the atoms have electron clouds around each atom, and those clouds tend to kind of overlap. Let's get to the meat of this lesson, and that is nomenclature of binary molecular compounds. Binary refers to 2, and molecular refers to nonmetals. So when we are naming binary molecular compounds, we are naming compounds that contain 2 different types of nonmetals. When we do this, we are forgetting any charges that these atoms might form when they're bonded to things like metals. Charges go pretty much completely out the window. What we do is we use certain Greek prefixes to indicate how many atoms of each element. But we never use the word mono on the first element. And we'll go through some examples of this. So you're going to want to memorize 1 through 10, the Greek prefixes. Mono refers to 1, di refers to 2, tri refers to 3, that should be a pretty easy one, triangle, tricycle, triceratops. Tetra refers to 4, penta, hopefully you recognize that as being associated with 5, hexa for 6, hepta for 7, octa for 8, that's an easy one, octagon, octopus has 8 tentacles, an octave has 8 notes, kind of. 9 is nona, and then 10 is decade, 10, and that kind of thing. The other rule, besides never use mono on the first element, is this. You want to write this down if it's not in your notes already. Don't use any prefixes if H is the first element. So, for example, these compounds here, and we're not talking solutions, we're talking the compound, we don't use any prefixes. We'll simply say hydrogen sulfide, hydrogen fluoride, hydrogen chloride. We don't use any prefixes. Let's try some examples. Carbon dioxide. The Greek prefixes tell us how many of each element. Carbon dioxide, 2 oxygens. This next one, CO, has 1 carbon and 1 oxygen. Remember that we never use the word mono on the first element. So this one is simply carbon, but then we do use mono on the second element if we need to, carbon monoxide. The next one is a fairly easy one, dinitrogen trioxide. Di means 2, so 2 nitrogens, tri means 3, 3 oxygens, N2O3. What would this next one be called? Dinitrogen, and what's the Greek prefix for 5? Pent, or penta, dinitrogen pentoxide. You could say pentaoxide if you wanted. It's not wrong, but it rolls off the tongue a little bit better if you just drop the A, pentoxide. The next one, carbon tetrachloride, is going to be 1 carbon and 4 chlorines. And the last one is going to be nitrogen triiodide. That's how you name binary molecular compounds. You use a Greek prefix to tell how many atoms of a given type. You never use mono on the first element. And if the first element is H, you don't use any Greek prefixes.